Students, let we start question number 5 of chapter Principle of Mathematical Induction. So this is given. So first of all, let Pn is equal to 1 multiply 3, 2 multiply 3 square plus dot 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 n multiply 3 exponent n, that is equal to 2n minus 1 3 power n plus 1 up plus 3 upon 4. So first for n equals to 1, for n equals to एक LHS RHS En is equal to 2n minus 1 3 plus 3 upon 4 for n equals to 1, for n equals to 1. So put there 2 multiply 1 minus 1 multiply 3 1 plus 1 plus 3 upon 4. 2 1 are 2, 2 minus 1 equal to 1. 3 power 2 plus 3 upon 4. 3 3 are 9, 9 plus 2 3 12. 12 upon 4, that is, so it is true for n is equal to 1. It is true for n equal to 1. Now consider it is true for n equals to k. Consider it is true for n equals to k. Pk is equal to 1 into 3 plus 2 into 3 square plus dot dot n into k into 3 exponent k is equal to 2k minus 1 2k minus 1 multiply 3 exponent k plus 1 plus 3 upon 4. Equation 2. Now for k plus 1, for n equals to k plus 1, put the value here 1 dot 3 2 into 3 square plus dot 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 k into 3 exponent k, and numbers will be added and replace k plus 1. So k plus 1 into 3 exponent k plus 1. So now use equation 2. Use equation polynomial of k plus 1. So use equation 2. Now for n equals to k plus 1, put the value of these, use equation 2. Use equation 2. Pk plus 1 is equal to 2k minus 1 3 power k plus 1 plus 3 upon 4 plus this k plus 1 3 exponent k plus 1. Take LCM. What is LCM? 2k minus 1 3 exponent k plus 1 plus 3 multiply 4k plus 1 3 exponent k plus 1. So 3 exponent k plus 1 is common. 3 is means here. 3 exponent k plus 1 is common. 2k minus 1. 4 multiply k 4k plus 4 plus 3 upon 4. So now 3 exponent k plus 1, 4k plus 2k 6k, 4 plus 4 minus 1 equal to 3 plus 3 upon 4. Now we can common 3 is common here. 3 2k plus 1 plus 3 upon 4. In multiplication power will be added. 3 exponent k plus 1 plus 1. So we can write like as 2k plus 2 minus 1. But can we change by 2 plus 2 minus 1 plus 3 upon 4. 3 exponent k plus 1 plus 1. 2 common k plus 1 minus 1 plus 3 upon 4. So according to the question, for the place of n, k plus 1 is here. For the place of n, k plus 1 is here. So it is true for equals to k plus 1. So by principal mathematical induction is proved. So it is proved for n belongs to natural number. Question number 6. 1 multiply 2 plus 2 multiply 3 plus 3 multiply 4, that is equal to and so on. So solution is this. Let En is equal to 1 2 multiply 3 3 multiply 4 dot dot dot. n plus 1 is equal to n plus 1 n plus 2 upon 3. So n plus 1 n plus 2 upon 3. So 4n equals to 1. 4n equals to 1. P1 is equal to 1 1 plus 1 1 plus 2 upon 3. 1 into 2 into 3 upon 3. So 2 comes here. So now from the first term 1 multiply 2 is equal to 2. It is true for n equals to 1. It is true for n equal to 1. Now consider it is true for n equals to k. K is equal to 1 multiply 2 2 multiply 3 dot 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 n multiply 1 is equal to, so n can be changed by k. Put the value of k at the place of n is equal to k plus 1 k plus 2 upon 3. Question number 2, 1 is there. So for now we have to prove that it is true for n equals to k. So for n equals to k plus 1. Take here 4k ek plus 1 is equal to 1 multiply 2 plus 2 multiply 3 dot 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 k multiply k plus 1 plus one term is major k plus 1 k plus 1 k plus 2 k plus 1 plus 1. At the place of these we put the value of these from equation 1. Use equation 2, sorry, equation 2. value of these k plus 1, k plus 2 upon 3, and k plus 1, k plus 1 plus 1, k plus 2. So k plus 1 and k plus 2 is common, both of them. K plus 1, k plus 2. K upon 3 r remains from here, and from here 1. So now take LCM. K plus 1, k plus 2, k plus 3 upon 3. So at the place of n, k plus 1 is here. K plus 1, n plus 1, k plus 1 plus 1, k plus 2, k plus 1 plus 1, 2, k plus 3 upon 3. So it is true for n equals to k plus, it is true for n equals to k plus 1. So it is by principle of mathematical induction, it is true for n equals to natural number. N belongs to natural number. This is the true relation for every natural number. So question 7, 1 multiply 3 plus 3 multiply 5 plus 5 multiply 7 plus dot 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 2n minus 1 multiply 2n plus 1 is equal to this. So a solution is, let Pn is equal to principle of n terms. N 4n square plus 6n minus 1 upon 3. So from this value, first of all we will prove that it is true for n equals to 1. For n equals to 1, P1 is equal to 1, Pn is equal to n 4n square plus 6n minus 1 upon 3. Now put the value of n. P1 is equal to 1 4 into 1 square plus 6 into 1 minus 1 upon 3. So 1 4 plus 6 minus 1 upon 3. 3 6 10, 10 minus 1 9. 3 3 are 9. So 1 dot 3. It is true for n equals to 1. It is true for n equal to 1. Now consider this relation is true for n equals to k. It is true for n equals to k. So pk plus 1, k plus, pk, 1 dot 3 plus 3 dot 5, 5 dot 7 plus dot 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 is equal to 2n, 2k minus 1 into 2k plus 1 is equal to k k 4k square plus 6k minus 1 upon 3. At the place of n we put k. Now we will prove that it is true for n equals to k plus 1. This is equation 2. 1 is here. This is equation 1. Anything you can write here. Now we have to prove that it is true for n equals to k plus 1. For n equals to k plus 1. K plus 1 is equal to 1 dot 3 3 dot multiply 5 plus dot 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 2k minus 1, 2k plus 1. Next term is here. At the place of k, at the place of n, we write k plus 1, 2 k plus 1 minus 1, 2k plus 1 plus 1. So at the place of these, we use equation 2. Use equation 2. The value of these k 4k square plus 6k minus 1 upon 3. So listen here. 2k plus 2, 2 minus 1 equal to 1. 2k plus 1 and this 2k plus 2 plus 1, 2k plus 3. Now multiply is there. 4k cube 6k square minus k upon 3 plus 2 the 4, 4k square. 3 1 4, 4 2 the 8, 8k plus 3, 3 1 the 3. Now take LCM. 4k cube 6k square minus k plus 3 4 the 12 k square 8 24k 3 3 the 9. Now 4k cube 6 and 12 18 k square plus 24 minus k 23k plus 9 upon 3. So now use remainder theorem. We will factorize of the all of them. So it is factorized by k plus 1. Write k plus 1 3 times upon 3. For making 4k cube, we multiply with 4k square here. Now 4k square we need 18k square. So 18 minus 4 is equal to 14. 14k. 14 1 ja 14. For making 23, 23 minus 14 is equal to 8, 9. So k plus 1, 14k, 4k square plus 14k plus 9 upon 3. Now we will convert into this formula. So 4k square plus 8k plus 1 plus 4. 8k, so 6k is here plus 5 upon 3. 4 is common from here. 4k square plus 2k plus 1, 6k plus 5. 5 can write we like as 6 minus 1. We are doing like this to making this formula. At the place of n, we want to change it k plus 1. So now your formula is 3d. 4k plus 1 whole square. 6 is common, k plus 1 minus 1 upon 3. It is your formula. At the place of n, k plus 1 is here. So it is true for k plus 1. It is true for n equals to k plus 1. So it is true for n belongs to natural number. 2 plus 2 multiply 2 square, 3 multiply 2 cube is plus dot dot dot, and 2 multiply 2 multiply n multiply 2 exponent n is equal to n minus 1 bracket 2 exponent n plus 1 plus 2. So solution is this. Let principal of n terms 4. First of all, we will prove that it is true for n equals to 1. For n equals to 1. So 1 minus 1, 2 exponent 1 plus 1 plus 1. So 0 multiply 2 equals to 0 plus 2. So for n equals to 1, it is true. 1 into 2 into 2. So it is true for n equals to 1. Now, by the statement of principal mathematical induction, it is true for n equals to 1. Now consider it is true for n equals to k. So pk is equal to 1 into 2 plus 2 into 2 square plus dot 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 plus k into 2 exponent k is equal to 2k minus 1, k minus 1, 2 exponent k plus 1 plus 2. This is equation 2. 1 is here. So now you have to prove that it is true for n equals to k plus 1. So pk plus 1 is equal to 1 dot multiply 2, 2 multiply 2 square plus dot 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 this k multiply 2 exponent k plus 1 into 2 power x k plus 1. At the place of these, use equation 2. Use equation 2. pk plus 1 is equal to k. At the place of these, write this value k minus 1, 2 power k plus 1 plus 2 plus this k plus 1, 2 exponent k plus 1. So this is common. 2 exponent k plus 1 is common in both of them. K minus 1 plus k plus 1 into 2 exponent k plus 1. So 1 cancel with 1, so 2k is here. 2 exponent k plus 1 plus 2. In the multiplication, power is added. So 2 exponent k plus 1 plus 1 plus 2. Now you can see, according to the formula, at the place of n, k plus 1 is here. K plus 1 minus 1 is equal to k plus 1. So it is true for n equals to k plus 1. Now principal mathematical. This formula is proved by principal mathematical induction. So it is true for n belongs to natural number. For every natural number, it is true. Now this is question number 9. Solution is this. Let Pn is equal to 1 upon 2 plus 1 upon 4 plus 1 upon plus 1 upon 2 exponent n is equal to 1 minus 1 upon 2n. So Pn 1 minus 1 upon 2n. So first of all, we will prove it is true for n equals to 1. For n equals to 1. P1 is equal to 1 minus 1 upon 2 or 1. So 1 minus half. 1 minus half is equal to half. It is true for n equals to 1. It is true for n equals to 1. Now consider it is true for n equals to k. Pk is equal to 1 upon 2, 1 upon 4 plus 1 upon 8 dot 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 1 upon 2 exponent k is equal to 1 minus 1 upon 2 exponent k. Now for n equals to k plus 1. So pk plus 1 is equal to 1 upon 2 plus 1 upon 4 plus 1 upon 8 dot dot 1 upon 2 exponent k. Next sum is here 2 exponent k plus 1. So we use equation 2 and put the value of this. Use equation 2. 1 minus 2 exponent. We can write like x 1 2 exponent 2 into 2. And the multiplication power will be added. So take a 2 exponent. So 1 upon 2 into 2 exponent. So 1 minus 1 upon 2 exponent k. 1 minus minus plus minus. So 1 minus half is equal to half. The multiplication power will be added 2 exponent k plus 1. So now it is true for k plus 1. It is true for n equals to k plus 1. Now it is true for n belongs to natural number. So it is true for every natural number.